Hello, dear students. Welcome to the channel and welcome to yet another new playlist in which we are going to discuss about the sampling and reconstruction. So, basically, we are going to continue our journey in the signal and system subject, and the journey led us to the discussion of sampling and reconstruction of different type of signals. So, uh, this is a little bit different from what we have studied up till now. In previous playlists we have discussed about different type of transformation which helps us to go from time domain to frequency domain. So we have discussed about the Laplace transform, Z transform, Fourier transform, and its different variants of these transforms as well. So if you want to know more about these transforms, if you want to learn about different type of transforms with numericals, you can click on the top right hand side corner of the screen. The link will be flashing there, so you can click on it and check that out. For this video there are no prerequisite. You just need to have a basic idea of what is a signal and what is a system, and I'm pretty sure up till now, if you are following this course up till now, you might have some idea about what signal exactly is. So without further ado, let's get started. Let us see what sampling is exactly. So now that all out of the way, let's get started. So the first thing that we are going to talk about is, if certain conditions are met, a continuous time signal or a CT signal can be completely represented by a recoverable form of knowledge of its value or samples, which are obtained at points equally spaced in the time. Now, there is a theorem which is called sampling theorem, which is used here. It is basically a property of of a continuous time signal. So this sampling property is used in a certain applications, such as in moving pictures, while in moving pictures which consist of a sequence of individual frames. So each of this pictures will be representing an instantaneous view, like a sample in a time, in the continuous changing scene. So when these samples are viewed in a sequence at sufficiently fast rate, we perceive an accurate representation of original continuously moving scene. And the sampling theorem, it lies acts it also lies acts as a bridge between the continuous time signal and a discrete time signal. So what happens exactly is, in many applications it is easier to process discrete signal because it is more flexible and it is more often preferred to processing the continuous time signal. And why is that? It is because the discrete signals are obtained due to the sampling can be easily processed by the digital technology system that are inexpensive, lightweight, programmable, and easily reproducible. So because of this sampling, uh, the use of the discrete time system technology in the implementation of continuous time systems becomes very easy, right? So basically the process of handling continuous time signals becomes very easy. So we use this sampling to convert this continuous time signal to a discrete time signal. Then we process that discrete time signal using the discrete time system, and then we convert it back to the continuous time system. And that's what pretty much we are going to discuss in this playlist. We are going to discuss about the sampling in very much detail. We are going to discuss about different type, like zero type and first type sampling as well. We are going to discuss a lot of things in detail about sampling, reconstruction, quantization, a lot of things. But before that, we are going to start. So we are going to start with the low pass and band pass signal. So what is a low pass signal? Basically, a low pass signal is defined as the signal which has the frequency spectrum extending right from 0 Hz to omega Hz. So if a signal sided spectrum is plotted and it is extending from minus omega to plus omega, if a double sided spectrum is plotted, as you can see in this image, the first image, then it is a low pass signal. What is the general example of a low pass signal? So a video signal which has frequency spectrum from 0 to 5 megahertz is normally the example of the low pass signal. Now what is a band pass signal? So the band pass signal are the signal which are having their spectrum extending from f1 to f2 with the value of f2 greater than f1, and both f1 and f2 are non-zero values. Like for example, the voice signals which are spectrum extending from 20 kilohertz to 3.4 kilohertz is normally band pass signal, and nature of these signals is completely different than the low pass signal. So does their application. They vary too much in normal operations. So as you can see in this image, the bandwidth is 2 omega, but it is centered about the frequency plus fc, as you can see here, plus fc and minus fc. And because of that, we assume that the value of fc is always greater than omega. So it is not basically w, it is omega. Don't it is misprinted over here. Don't get confused in that. Now let's discuss about the sampling process, or what exactly sampling process is. So basic definition has been given here. Sampling process can be defined as the process of converting a continuous time analog signal to a discrete analog signal, and it is sampled in the discrete time representation of original analog signal. So to understand the sampling process in a better way, let me show you this picture. So at input or the input of the sample, we apply analog signal, and its output will be the sampled version of the input signal. And this sampled signal represents the original analog input faithfully if the sampling rate is uh, smooth enough. Now you may have a question, why do we need this sampling? Why do we need to do this sampling? So if you are familiar with pulse modulation, and I believe most of you are pretty much familiar with pulse modulation, it can be any type of pulse modulation, and basically digital systems as well. So if you are familiar with pulse modulation and digital modulation systems, the signal to be transmitted needs to be in the discrete time form only. You cannot basically process the continuous time signal. It must be in the discrete time format. So if the message signal is coming from a digital source like a digital computer, then it is in the proper format, or it is convenient for a digital communication system to be to process, which may look something like this. But that's not always the case. Life is not easy. So the message signal can be analog in nature. It can be speech, it can be voice, it can be video signal, it can be anything. And in such cases, it has to be the first convert it first need to be converted into a discrete time signal, and we use the sampling process to do this conversion. And thus we use the sampling process. Using the sampling process, we convert a continuous time signal into a discrete time signal. So now you have an idea why when did I said that we are basically converting continuous time signal into a discrete time signal. That this is what I meant. Now let's see the third point, or the points which I want to discuss in the requirement of sampling. Coming back to the technical stuff, four things: input signal, sampling signal, output signal, reconstruction. All four signals are same, no difference. We are just processing these signals. So for the sampling process to be practically unity, it is absolute requirement to choose the sampling rate properly, and that is why the input signals are very much important. The input signals x of t, or whatever signal you want to take, it should be band limited signal, which means the spectrum should exist only between 0 and some finite frequency, let's say omega. The second one is the sampling signal. Once you decide the band limited signal, or once you decide the sampling rate, you can send the signal for sampling. And a sampling signal, let's call it s of t, as for sampling, is a train of unit impulses spaced by a period of t or ts seconds. This sampling function samples the input signal at a rate of f of s samples per second, and based on that you will get the sampling time period t of s, which will be exactly inverse of the f of s. After that we get our output signal. Once we decide the sampling time, we get to our output signal. The output signal is the sampled version of the input signal, and it is a discrete time signal which is represented by x delta of t. The output signal is obtained by the multiplying the signal input signal with the sampling signal in the time domain. So x delta of t, which will be equal to x of t into s of t. Once you get the output signal, you absolutely need to convert it back to whatever form it was. That thing is called reconstruction or recovery. So reconstruction or a recovery is a process of recovering the original signal x of t from its sampled version. What was the sampled version? It was x del of t or x delta of t. So for this, for the reconstruction, the sampled signal x delta of t is processed through an ideal low pass filter with gain t and the output frequency greater than omega. And in the result, we will be getting our original signal. But hold on a minute. You might think that okay, sampling is very simple. It is not that simple, because you need some important requirements and some conditions required to be fulfilled in order to sample your signal. So first, the sampled signal should be represented the original signal faithfully. It is the must requirement. If it doesn't happen, then your message or the information in the signal will may get suffered, and we should be able to reconstruct the original signal from its sampled versions. So you're not allowed to take too much samples, and you're also not allowed to take too less number of samples. The number of samples should be good enough that you get the original information back as it was. Now let's see what the sampling theorem tells us. What is exactly a sampling theorem? So now, in order to represent the original message or original signal faithfully without loss of any information, when I say faithfully, I mean without loss of any information as it was originally, it is important to take as many samples of the original signal as possible. The more the number of samples you take, closer the representation will get. And this number of simple samples will be dependent on the sampling rate and the maximum frequency of my signal to be sampled. Once we get through this two of these variables, we can come to the sampling theorem. Basically, the sampling theorem statement is divided in two different statements, and by converging them, we get to the final statement. So, let me first discuss about those two samples, two statements. The first one tells us if if a finite energy signal x of t contains no frequencies higher than omega hertz, which means it is a band limited signal, then it is completely determined by the specifying its values at an instant of time which are spaced by half omega seconds apart. That was the first statement. Second statement is if a finite energy signal x of t contains no frequency components higher than omega hertz, then it may be completely recovered from its samples which are spaced 1/2 seconds apart. Understanding this, those two statements are close to each other. Now, when we combine both of these statements, what we will get? We will get this statement which sound like this and which look like this on your screens. A continuous time signals a continuous time signal x of t can be completely represented in a sample form and recovered back from its sampled form if the sampling frequency fs is greater than or equal to 2 omega, where omega is the maximum frequency of the continuous time signal x of t. Now I'm sure you might be clear, you must are clear with the sampling theorem. Now we have to prove it. We have to prove the sampling theorem. So let's see how we can prove the sampling theorem here. So the we need to make some assumptions in order to prove this sampling theorem. First, the first assumption is x of t is a continuous time analog signal, or you can see this signal. Let's assume my signal looks like this. It is a continuous time analog signal, and here you can see this value and this value and this value all are same. One cycle is getting completed over here, and let's say x of t be a signal with a finite energy and infinite duration, right? Because it is a continuous time signal and it is a signal with finite energy and infinite duration. Let's say x of t is a strictly band limited signal with a maximum frequency of omega hertz. So it is a band limited signal and the frequency is omega hertz. It will get repeated at every omega instance. Let's s of t be a sampling function, and it is a train of equally spaced unit impulses. As you can see here, it is a equally spaced unit, it is having equally spaced unit impulses by a period of ts second. The difference between them is ts, difference between two instances is ts, and hence the sampling rate of sampling frequency is equals to 1 by ts, right? F of s will be 1, fs will be 1 by ts, where ts is the time duration or the repetition or the instance between time instance between two impulse trains. And when we sample them, we will get something like this. Basically, we are multiplying our continuous time analog signal with the train of impulses. It looks very simple, but we actually are following 7 different steps to get here. Which are the 7 different steps? Here they are. The first step says the represent the sampling function s of t mathematically. In second step, we have to represent the sampled signal x of delta t mathematically. Then we have to obtain the Fourier transform of the sampled signal. Then you have to prove that the sampled signal x delta of t completely represents my original signal x of t. Then we have to represent my x of t as a summation of the sinc functions. That is called interpolation. That is something we are going to see in upcoming lectures. The 6 steps tells us the graphical representation of the interpolation process. That is also what we are going to see in the upcoming classes. And the 7th step says the actual recovery of x of t using an ideal low pass filter. How do we do that? So that is also we are going to see in upcoming classes. Today we are going to discuss 2 to 3 steps. let's come to the first part. We have to obtain the spectrum of my sampled signal, right? So uh, the first step of the first part is to represent the sampling function as s of t mathematically. Now how do we do that? So uh, you can say from that figure, this figure, what we are basically doing, we are doing here, we are basically multiplying it, two signals, right? So the sampling function s of t, which is a train of unit impulses of period t of s and frequency f of s, the sample function s of t can be represented mathematically with the multiplication of both of them using this. S of t is equals to summation n equals to minus infinity to infinity delta t minus n of ts. The next step is to represent the sampled signal x delta of t mathematically. So again, as you can see in the first image, the sampled signals x delta of t are here. Sorry, sampled signals are here, and it is presented only at the sampling instant ts, ts, 2ts, 3ts, and so on. So its instantaneous amplitude is equal to the amplitude of the original signal x of t at the sampling instance, right? And here these points, this circular points you can see here are the encircled points at which we are getting a sample. Now if we want to represent the instantaneous amplitude of x of t at various sampling points, let's say t is equals to nt of s as x of nts, we will be following these encircled points. And looking at the sampled signals, let's come back to here. Looking at the sampled signal x del of t, we can say that the sampled signals is obtained by the multiplication of x of t and s of t. Pretty straightforward, right? What is the value of x del of t? It is basically the multiplication of x of t into s of t, which is basically x n of ts into s of t. Now, if I want to use any other values, let's say from the very first, from this one, we know the value of s of t, right? So if I substitute the value of s of t in here, what I will get? I will get something that will look like this. X delta of t will be equal to summation of n equals to minus infinity to infinity x of n ts delta t minus n ts. So I hope it is very much clear. Again, pretty much straightforward, no big tricks here. The third step is to obtain the Fourier transform of a sampled signal. And the Fourier transform of a train of impulses is, we know we discussed this in the property of Fourier transform, remember? So it can be given as x of f is equals to f0 summation n equals to minus infinity to infinity del f minus n f0. And based on that, the Fourier transform of sampling function will look something like this, right? No new things here. Instead of f of 0, we are taking f of s. The sampled signals in the time domain will be represented using this. This is something that we already know. We are taking product of x of t and s of t, just like we did in this last previous step. And then we will be taking the Fourier transform of both the sides. So x of del of f will look like the multiplication or the convolution of x of s and s of f. When we substitute the values of s of s in this equation, we will get something like this. X of del, sorry, in this equation. this value we will be putting this value in this equation. So we will get x del of f is equals to x of f in convolution with or multiplied with f of s summation n equals to minus infinity to infinity del f minus n fs. Now we all know that we all have studied the properties of convolution in previous classes. If you, by the way, if you haven't followed the previous playlist, you can find the properties of convolution and details about the convolution in that classes. So you can click uh, you can find it in the description below, or you can click on the top right hand side corner of your screen and check it out. So based on the properties of convolution, when we interchange the order of the convolution and convolution and summation results, summation will be same, there will be no change. And from the properties of the delta function, we can say that the convolution of x of f x of f and the delta f of n of n f minus n fs will be same as the x of f minus n fs, right? That we studied in the properties of delta function in the very first or second chapter. And based on that, we can simplify it, and what we will get will x of delta f will be equal to f of s summation n equals to minus infinity to infinity x of f minus n fs, where my x of f will be the Fourier transform of the original signal. Now coming to the conclusion of the equation we just derived, the term x of f of n x of f minus n fs in the previous equation is basically a shifted version of the spectrum f of x of f of original signal f of t, and that depends on the value of n exactly, which extend from minus infinity to infinity is going. And if it's going if it is indeed going from minus infinity to infinity, then we will get infinite number of original spectrum x of f centered on different frequencies, like 0 plus fs minus fs plus 2 fs minus 2 fs and so on. So the concept will be clear if we open that previous equation, and when we do so, we can separate the different terms by opening the summation sign. And when we do so, we get equation which looks something like this: x del of f of f will be equal to f of s into f of s into x of f plus summation n equals to minus infinity to infinity, which does not equals to which does not include x equals to 0, fs into x f minus n into fs. So you will be getting something like that. And uh, you can see in this image here, it gives you a better idea that here we are having x of f shifted right by fs, then we are having the spectrum of x of f itself, then we are having the spectrum of x of f shifted left by f of s, and then we are having the spectrum of x of f shifted left by 2fs. So that is basically your x of delta of f. Now let's let's come to the part 2. Before we go to the part 2, take a look at this image, figure 8.2.2. You can see the first image on the in the middle, this one, it is showing the spectrum of the original signal x of t, and we discussed earlier that it is a band limited signal. And the image below is showing the spectrum of the sampled signal x del of t. with fs is equals to 2 omega. So here you are having fs xf, here you are having fs xf minus sf, you are having fs x f plus fs here. So you can see the spectrum as well here, and from that we can conclude that the process of uniform sampling of the signal is in the time domain result in the periodic system in the frequency domain with the period equal to the sampling rate. Now let's move to the second part. uh, the second part says to prove the sampled signal represents x of t. So first we have to again obtain the Fourier transform of the sampled signal, and here we have shown the sample signal one more time here. Now we all know the formula of Fourier transform. Before going there, we can also say that x delta of t can be represented as the summation of various signals, which may look something like this. X delta of t will be equal to n equals to minus infinity to infinity x n ts into delta t minus n ts, right? And we can represent it in different form as well, right? The form which will look something like this. I'm not going to discuss it into the detail. And now that we know the formula of x delta t, we can obtain another useful expression for the Fourier transform x delta of f by taking the Fourier transform of both the sides of the equation. And that equation will basically the multiplication of this term, the whole term, into the e raised to j 2 pi nf into ts. You know the basic of Fourier transform, right? We studied in the previous playlist itself. So that equation of the Fourier transform of discrete time signal will be just the multiplication of those two signals. Now we have to obtain the Fourier transform of the input signal, and that is why it is also called DFT, discrete Fourier transform. So what do we do here? We compare it with the definition of Fourier transform of continuous signal. What is the definition? And when I say definition, I don't particularly mean definition, I mean the formula. So formula is, if you all remember, x of s equals to minus infinity to infinity x of t into e raised to minus j 2 pi f t into dt. That was the formula. So as a signal is as a discrete signal, the integration sign has been replaced by the summation, because we are taking the discrete signal. So instead of integration, we will be taking the summation, right? If you remember the discrete Fourier transform as well, we have discussed discrete Fourier transform earlier. So the equation will be this: x of del will be fs x of f. We are repeating what we did previously, what we did here. No, not here. Why did we do it here? What we did here at here as well. So again we will be ignoring n equals to 0. We are including it over here, and then we are representing the remaining signal. And the Laplace, the Fourier transform of n equals to 0 will be 1 by fs into x delta into f minus the whole term, the Fourier transform of whole term. But there is one catch. In the range of minus omega to omega, the second term of this equation will not be represented by x of f equals to 1 by fs into x delta of f. We have to substitute fs is equals to 2 omega, and then x delta of f. From the equation we can write this way: xf is equals to 1 by 2 omega summation n equals to minus infinity to infinity x of n into ts into e raised to minus j 2 pi n f into ts. and it is pretty much the frequency spectrum of x of t in terms of x of nts. What what's exactly a sampled signal, and when we substitute the time, what was the time, 1 by 2 omega or half omega, we can get x of f, which will look something like this based on the formula. Now there's a few things which we have to take care of. The first thing, the equation, this equation, the last equation, it is showing the spectrum of x of t, and it is the same as the spectrum of x del of t in the frequency range minus omega to plus omega, which means the sample signal will be representing the original signal x of t successfully, and because of that the sampled values x of n by 2 omega of the signal x of t are specified for all time, and then Fourier transform of x of f of the original signal is uniquely determined by using its previous equation, whatever equation we had. Now because the time domain and frequency domain are related, basically x of t is will be related to x of f by the inverse Fourier transform, and it follows the signal x of t itself uniquely determined by the sample values, right, for n going from minus infinity to infinity. uh, if I want to make it simple, or if I want to say it in other words, the sequence of the sample x of n divided by 2 omega will contain all the information of x of t, which means basically we are not losing any information, and thus we have proved that second part of the sampling theorem is correct. So in the upcoming classes we are going to discuss about the recovering using low pass. We are going to discuss about the sampling with zero order hold and first order hold, and we are also going to discuss the interpolation. So pretty much things to come, so gear up. If you have any doubts, any queries, any feedback, any suggestions related to the channel or the class, please feel free to mention them in the comment section below. I will try to address as many of them as soon as possible. We will keep this lecture till here, and I will be seeing you next time with the new contents, and uh, we will discuss continue this discussion further. So till then, thank you very much for listening and take care of yourselves. Goodbye for now.